What's up, YouTubers? So I'm up cleaning my shop out and moving everything out, and I hate moving. I don't think anyone loves moving, and any excuse I can find to not move shit out is like high on my priority list. So I found this and I thought, well, I got to put this in another bin over there anyways, because this thing is literally like 120 pounds and is going to tear right through this pretty soon. So I thought I would sort through this into that bin over there. And why not talk about some of the welds on this stuff? Now, most of the welds on this crap is all going to be pretty decent because, well, I welded it and I never make bad welds, right? Yeah, I don't think you believe me, but whatever. So we're going to go through some of these. We're going to talk about the finer details. I'm sure there's some dandies in here that we can all learn something from. And we're just going to take it easy and see where this video goes. So grab yourself a drink or some popcorn or something and let's get into it. All right, so I'm just going to grab little chunks of stuff here and we're going to talk about what we see. This was on some video I featured, probably looking at penetration. Well, you can't really see much of it anymore. It's aged due to the humidity and stuff down here. Overall, this weld profile, this is a stick weld, pretty acceptable. The main thing we're looking for is slightly convex. And if you look at that, I'll bring it up to you. We're looking for slightly convex. We don't want to see concave where it's very thin in what's called the throat of the weld. We don't want to see too much undercut, like we got undercut right here. Very clear evidence. But as far as acceptability, these stick welds don't look too bad. Clearly it's a 60-10, 60-11 rod, something in that. Not too bad. We don't see excessive spatter. We don't see tons of slag inclusions. And trust me, we'll see some welds with some slag inclusions. So if you don't know what that is, either watch the video I have on that or just wait a few minutes here. So that's, I would say, decently acceptable. Nothing really too bad with that. So let's come over and grab another one. So here, stick welds, this was from, I believe, my 7024 video series. We can tell massively wide welds. So this was either 7024 or very big 7018 rod. The profile of it, just looking at the side shot, very, very wide. Massive welds. Don't really see too many defects in them. Don't see tons of spatter. Now, focusing on this, which is essentially a form of a lap weld, we can see that there's some almost over penetration or over melt through on this edge of the plate where you can see the bead, rather than hitting just the edge of the plate, melted up over. Is that a defect? Well, for stuff you're doing at home, probably not. You can just take a grinder and clean this up and make it look better in about 5 seconds. But, depending on what you're welding on, you may not be able to, get it to melt over the edge. That may be considered a defect. All depends. This side is significantly better, but even so, you can see it kind of melted through this. But the original plate edge is somewhat there. Again, not too bad. No excessive spatter. There's some. Let's move on here. Something a little bit different. Not really sure what this is or where it came from, but we got some ugly welds, and I'll be honest, I don't believe I had anything to do with this. Probably somebody was teaching how to do spot welds or something. Not really sure, but we have one somewhat decent looking TIG weld, but then this, if you look here, we have what probably is porosity. You can tell just by the look of this, if your weld looks like this, is dull gray cooked, this pretty much means one of a few things. One, definitely you were running too hot, or you didn't let this cool down and just ran a bunch of passes. And two, that your shielding of your inert gas or whatever wasn't very good, because when you start getting this scale like this, I'll bring it up for you to see better. That scale is just like what you find on hot rolled mill scale on steel. It's basically reaction of the steel with oxygen. And the only way you can get scale like this is for this to be red hot and then be exposed to oxygen. So like I said, excessive heat and then also exposure to oxygen in the air. It almost seems, yeah, I don't know. For a second, I thought this might have been a plate of titanium, but good God, I hope not, because it's like 30 bucks worth right here. Yeah, I don't know what that's for, but clearly a lot of bad welds on here. Again, same deal here. You can see just excessive heat. You can also tell if you look at how flat this weld is, like there's no filler in it at all. Like you can see there's some filler here, which this is really too small of a weld, but there's no filler, super hot because it's wide, all bad things. Yeah, interesting. I don't know where that came from, but terrible. Here's a fun one. I didn't actually shoot this doing this, but this is a piece of 5/8 thick aluminum, so real thick aluminum. And maybe I had it in some video, maybe not, I don't remember, but I was showing that with a 210 amp TIG welder, you can weld aluminum this thick, but you got to preheat it super hot. And I did 3 welds on this. This was at like 210 amps, and if you look at that, like literally not really wetted out that good, very small weld, and then once you preheat it, how much different it welds. Well, this down here is a prime example. Let me clean some of that off. So this is probably the best example of a bead of caulk on plate I've ever seen. So what you're looking at here is this was done with an aluminum stick rod. I bought a bunch of aluminum stick rods. I did a couple videos related to it. I actually did one repairing something on a tow truck that was out of aluminum, and I never released it because I lost some of the footage. But in that video, I used this plate as just a test to see what would happen if I set the rod at 130 amps and just tried to run a pass on cold aluminum. And well, I found out this is exactly what happens. Like literally, I could probably take a hammer, hit it here, and this would just chip off. You know, look at that. So this is a prime example of a very cold weld. This did not have proper heat input. And yes, this is aluminum. Same thing can happen on steel. Same thing here. Look at that little pride and joy of mine there. Terrible, you know. Had I preheated this plate, the same thing that you see here happened, where it went from super narrow, a little bit crowned up, to much flatter, wetted out better, would have happened here. If this was 500 degrees, this would look nothing like this. But that's a great example. Extremely cold, hot, like within the range. All right, let's keep moving. So this, I don't remember if I did push and pull with MIG, but this is another good example how we can fine-tune our welds. The weld on the right doesn't have noticeable spatter, and in the weld on the left, you can see significant amounts of spatter. That could be an indication that our wire feed and voltage are not in line to what they should be, and this was MIG welded. And it could also be the difference between pushing and pulling. Pulling sometimes can create more spatter, and I'm not for sure on that, but judging by, yeah, I must have pushed this and then I must have pulled this. So this weld looks better than this one. Now the other thing, you see how you can see a shadow down here? And how it's kind of like, you look here how nicely wetted into this bottom plate that is, like, look at that, and then you start seeing shadows, and how it's, if we do a side angle here, they call this cold toes. That's welder speak for the edge of the weld is cold. The most common cause of this is just simply not running enough heat. So in the case of MIG, not enough voltage. In the case of stick, not enough amperage. But if you travel too fast, that can also contribute towards it as well. And I think that was a main culprit here. I started, and then I started moving too fast, and once I slowed down, it filled in nicely, but cold toes there. This, overall, I would say looks good. No real issues there. Never welded the backside of that, whatever. Let's keep going. So I remember welding this. This was on a video where I ran the same amperage. This is a stick weld. And same amperage. All I did is I ran as consistent as I could for this weld. And for this one, I was not consistent at all. Just to kind of prove the point how much it matters to just be consistent on your travel speed. That's the difference. Like, there's no magic between these two. It's just this, my travel speed stayed the same start to finish. My rod angle, my arc gap, all the same for that. This was all over the place, and look what you get with that. We can see other weld defects. We have evidence of porosity here. There's undercut here. I mean, it's an ugly looking weld. There's no way to put it but that. So right here, it's like, well, what do you fix there? Well, let's be honest here, guys, everything. Everything is wrong with that. But that's all right, because any one thing you change for the better will give you a better result. I mean, granted, everything's wrong, but one or two things fixed make a huge difference. Down here, I don't know why I did this, but I welded this plate to this. That looks very acceptable weld. I blew the corner out a little bit. Oh, actually, that was because of the back side. I blew it out. But I don't see, I don't see any evidence of cold toes. Let me get you where you can see. It's flowed out real nice. So yeah, that looks good. The back side must have been welded with, I don't know what rod. That's definitely maybe 6011 run hot. I'm not sure on that. We have slag up here that I didn't clean, but maybe it was flux core wire that I welded that with. That doesn't look like flux core wire, but yeah, so those look all right. Now, these, I don't remember what I was doing. I think this was just another comparison of not doing things right. Like, the little minor details will completely change the way your weld looks. So those are, what does this tell us right here? Like, if you just saw this and someone just put these down, you would say, okay, well, their travel speed is inconsistent and their settings are likely a little bit off, but the first step would be to try and be more consistent on travel speed and then go from there. All right. We've seen those. Here's a little thinner material. This is like 3.2 millimeter. I believe this was flux core wire. It may have been MIG. It's hard to tell. We can see that the profile of these, I mean, it's fairly acceptable. Like, this is clearly hotter than this one because of the way that it's humped up. But most of these aren't too bad. This is a little bit colder. Like, use shadows to your benefit. Like, you see how you tip this down and you start seeing a lot of shadows? It's kind of telling you that your toes, like the weld is humped up like this, and you're seeing a shadow because it just didn't wet out that well. We got like porosity here, air bubble that failed to escape, gas bubble, and we blew off the end. So this here settings are more of an issue. They're not in line, or travel speed isn't. Don't be afraid either on clean material. If you see, you know, your heat affected lines like this, they tell you a ton. You know, you look at how this weld here and how close the heat affected is, that's going to tell me that this is a colder weld than this is, because if you split the weld down the middle and then measure the distance there, it's further than this. So that's telling us that this was run hotter potentially than this. I mean, they look on this side fairly similar, but you get the idea. Like over here, there's no question. I mean, the heat affected zone is way wide on that. And well, much like you would expect, it blew it out. look at a couple more in here, see if I can't find some. All right, here's an interesting one. So again, this is stick welding. This is a 3.2 millimeter 1/8 inch plate. What do we have here? We have a botched restart. You can see the divot wasn't filled. That's not a good sign. Again, use shadows to your advantage. What do you see when you see here? You see a ton of shadow over here. Less here, but that's telling you that that bead is really humped up. And when we look at the side profile, see how that's humped up? That's a good indication that we could have used a little bit more heat, so a little bit more voltage or a little bit more amperage to get this to wet out better and flatten out and get that toe section of the weld to fuse a little better. Now, let's be honest, is this a terrible weld? No. Would this, if you had this like on your car or something, would it fail? Probably not. I mean, if this is going in outer space, this would be unacceptable simply because everything is so expensive, you can't risk failure. So no, space shuttle, no. Is it good enough for something in your yard or on your tractor? Maybe. When we look over here, don't mind, I don't know what this junk is right here. It must have been, who knows. But when you look at like this, you see how nice and clean that toe line is, and then it's nice up here. When you look down it, you see how it's like nicely rounded over. We don't see like really dark shadows. This is much better, same thing down here for the most part, than this, so a lot to learn there. All right, let's keep going. Let's look at a few more. Well, there isn't much to look at here. This is actually just one of my plates I keep on the table when I do artwork so I can check that the gas flow and everything is working. But it's still kind of cool to look at. Maybe I got something here. This is more useful on this side. So this is TIG welding on stainless steel. So this is pretty thick. It's over 1/8 inch material, and this is 304 stainless. Now, stainless steel, which I haven't done a video on it, and I will in the future, stainless steel tells you everything you need to know and how the weld looks. When you look at something like this, you see how nice and silver goes to straw. Ideally on stainless, you want pure silver welds. In the real world, it's extremely difficult to achieve that because it has to do with the temperature that the stainless is, that the weld that you deposited is, when it's exposed to oxygen. Well, at any temperature, like any amount of heat, it tends to turn yellow or straw first, then your like reds like you see here, and then it goes to kind of like a purplish, then blue, then light blue, like this is light blue, then like no color like this, and then it goes dull gray. Now it all depends on what you're welding. If this was food grade, most of these would be unacceptable for the oxide. Now, you can passivate and clean this off. Like I could actually mechanically wire brush this to clean it, but in sanitary type situations, they'll clean this with like an electrolysis process to clean this off. But you can't, if it's dull gray and cooked, like I don't really see any on here that are a good example of that. Like if you look here where it was plasma cut, if your welds are dull and gray and look like that, you can't passivate that with a cleaning solution in like an electrolysis machine or whatever they're called. So that would be completely unacceptable. A lot of this you may be able to clean up, but again, it all depends on what you're welding it for. Now, TIG is much, much harder to tell. When you look here, and I'll bring this way in here, you can see evidence of cold toes or just lack of consistency in TIG. It's just so much more minor than what you see with stick and MIG. I mean, you see how you still see the same evidence. At the start, this is a little bit humped up, and then it flows out wider. This is because the amperage was too low, and then the weld got moving. And you'll actually see, it's going to be very difficult. This is more humped up here, and then it flattens out. But again, it really doesn't matter the material you're welding. All the signs are the same. It's just with stainless, the color tells you so much. The other interesting thing I'll mention on this before we move on is if you look here, you notice how this heat affected zone, the has zone, is so close to the weld. And then when you go and look at like clean steel, like this piece, you see how much further it is out? This color here on the side of the weld is the same thing as here. The difference is stainless steel is a very sluggish heat transfer material. It does not transfer heat very fast, and that's why it actually welds at lower amperage than steel does, because your weld pool gets hot and stays hotter because the heat's not dissipating through the material as much as steel. Whereas the opposite, aluminum, transmits it so well that you need a ton more heat. But that's essentially what you're seeing here is the same as this. It's just much closer to the weld. Pretty interesting. Well, let's look at like two more. That's kind of boring. There's got to be some good one in here. Here we go. So, perfect. This will work real good for what I didn't really cover. So this clearly is stick welding. This is thick plate over 5-6 millimeters, so 1/4 inch or so. When you start looking at this, and you may see this in your welds, let's start at like the best out of these three. I would say this out of these three is probably the best. And you can see again, shadow lines, probably cold toes. It's fairly inconsistent start to finish, but out of the three of these, it's, I would say, the best. When we look at this one, there's restarts apparently, or at least that's what it looks like. Those are pretty rough. The overall bead appearance, you know, it's just, again, consistency isn't here. Looks very rough. But then we got this dandy right here. And honestly, I won't take credit for making this. I think I was teaching someone how to stick weld, but maybe it was me. I don't know. But now some of this is just slag that's still in there. You can see it'll clean up. Whoop, bumped the camera. Yeah, there's still, so that's not porosity, that's just slag. But there is slag inclusions here where like the weld went around the slag, and then the slag right there is stuck in there. So again, what do we see here? Very inconsistent weld, both in width and height. The profile of it is like humped up, it's flat. I mean, everything about that does not look good. Now, it's a great question to ask yourself, would this weld fail? Well, I've seen worse welds than this on trailers, and they've held up, but it comes down to, it really depends. You know, if I put this weld down myself, you know, I got a fair amount of pride, and, you know, I will honestly say I would grind it out with a carbide burr or a hard rock wheel on a grinder, and I would re-weld it. I mean, shit like this happens. Trust me. I've put down far, far worse than this many a time, and even nowadays, it's not impossible for me to put down a weld that's far worse than this. I mean, shit happens. It's more about what you do when shit happens than the fact that you think you're never going to have it happen to you. Let's look at the other side on here. yeah, I'm not really sure. I don't ever remember doing this, but so we have evidence of undercut here. It's going to be a little difficult, but you see how like the weld sunk in there? That's a great example of probably running too much amperage or too long of an arc gap. Like if you can grab the edge of that and it's sunk in, that's undercut. We don't want that. Gives a failure point for a crack to start, weakens the metal, etc. I don't know what that is down there. It looks like a beehive. Now this side, and I'll try and get the light better for you. This, if you look at it, the weld is like 90% on the bottom plate and almost nothing on this side plate. So that's a poor rod angle caused that. You know, that's the rod was coming in like this rather than like this. So is this a defect? Absolutely. If this plate were to get bent over towards this, like this, it would, you know, we have a very thin weld there, very weak. We don't want that. And here's the best I've seen so far for slag inclusion. So if you see here, the weld just deposited down here and over and completely just went around this. That's very common with 6013 rods, or if you run a rod at the wrong angle or too low of amperage. So that's, again, defect, no good. Now this, other than undercut, that looks good. This one, again, botched restarts, huge divot, generally undesirable divot, cold toe. This is a, yeah, we can see evidence of, see all of that, like that clear line there, that it's a shadow, that's all undercut. You know, use light to your advantage to look at it. Now, some of this is just slag still on the edge, but I mean, look, I can grab it with this and it doesn't come out. That's undercut. All right, let's look at one more. Screw it. Let's look at this guy. I remember welding this to test whether or not you can weld on rusty plates. And I did it with 6011 and 6010, or no, excuse me, 6010 and 7018. We can't, yeah, we can actually still see the penetration. Look at that. It's like 6010 just uses the rust as more fuel to burn in there. Both of them are acceptable, but look at the penetration difference on that. 6010, 7018. But the overall bead appearance of this 6010, pretty rough. It's hard to tell if there's any undercut in this top toe and bottom toe just because there's still unclean slag and mill scale on there. So you can see like 6010 is a difficult rod to determine, you know, weld defects on. There could be some in there. I know it looks fairly ugly, but again, that had a lot to do with the extremely poor prep. You know, if you're trying to gauge if your welds are looking good or not, and this is what your base material looks like look at this. Like, it's not even worth, oh, is this weld, you know, good or not? Well, if this is your material prep, forget about it. Don't even waste your time. The interesting thing is, though, this weld here, very clean looking. Top toe here's not quite wetted out that well. You can see, again, uses shadows so we can see that. But overall, I would say that's a very acceptable looking profile. It's a little bit low. It's a little bit down here. You know, always pay attention to that because it's thinner here. So if there's stress on this plate bending it over, not much metal there's holding it on. But let's face it, on this thick of 1/4 inch material, this would probably be better suited to a 2 or 3 pass weld or a bigger rod than what I use to do a single pass. All right, interesting stuff there. This video is already longer than I expected. I don't know how I can talk for so long about stuff like this, but let's go to the conclusion. I almost forgot before we go to the conclusion. Like I said, all welding has the same similar characteristics between like cold, hot, or, you know, acceptable welds. And TIG is the hardest to determine simply because oftentimes the welds are so small, you're talking about minuscule differences. But I wanted to show you on this pineapple on stainless steel I welded, you can still see the same things, just much, much more minute. When you look at this weld here, you see how it's slightly humped up, it's very narrow. And then you start looking at some of these other welds, like this would be a good example. See how it's wider a little bit? Like we'll even look, let's see here. Like this is wider, this is narrower. Okay, this has less heat in it than this. I mean, they're all very, very, very close, but like this is wider, this is narrower than this, so more heat or slower travel speed, less heat or faster travel speed. And when we look up here, again, all the same kind of things. See how wide this is? And then look how narrow this is. Notice how wide the heat affected zone lines are versus here. Less heat, more heat. So you can see all of that evidence even in the most minute, smallest welds, and it doesn't really matter the process. And when you see that, you can actually do something about it. So let's actually go to the conclusion now. So what did we learn today, guys and girls? Well, we learned a little bit more about how to read our welds to become better welders. And I'm not going to go through this whole pile, like you could spend days doing that, analyzing stuff, but I think I covered enough to where you'll get a better idea of what you're looking at. And the key takeaways really is that if you see your weld humped up or narrow, probably use a little bit more amperage or a little bit more voltage if you're welding with MIG, or slow your travel speed down. And if that weld is way flat and there's like no reinforcement or no weld metal, then, well, with wire, you need more wire speed to feed more wire in. With TIG, you need to add more wire, and with stick, you probably just need to slow the hell down. But yeah, I mean, there's so much to learn in everything you do. You just have to spend a couple minutes and look at what you did and then determine where to go. It's more important to know what to do to make things better than it is to not make mistakes, if you catch what I'm saying. So anyways, with that said, thanks for sticking around. Till next time.